Hello and welcome to Lecture 20 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to calculate the concentration of free electrons. Okay, so last time we learned that there are two types of charge carriers in semiconductors. There are free electrons, which are electrons in the conduction band, and there are holes, which are an absence of electrons in the valence band. So since the electrical properties of semiconductors are heavily dependent on the concentration of charge carriers, we need to find an explicit expression for these concentrations. And that's what we're going to find in this lecture. So in this lecture, we're going to derive a major result in the physics of semiconductor devices, and we're going to carry this result until the end of the course. So this is a very important lecture. So before we talk about free electrons in semiconductors, let's imagine that we live in a magical land which I call magical semiconductor land. And in this land there is a classroom and there are magical chairs in this classroom. And these magical chairs, they have a 50% probability of finding a student sitting on this chair. And I'm representing the chair with this square here. Now, if I ask you how many students you're going to find in this classroom, you cannot give a precise answer because half of the time that you take a look at the classroom, you're going to find a student in the chair, and I'm representing the student here with this blue ball. But half of the time, you will not find a student in the chair. So if I ask you how many students are in this classroom, you cannot give a precise answer. You can guess 1 student or 0 students, but you're going to be correct only half of the time. And if there are 2 chairs in the classroom, we still cannot have a reasonable guess, but at least we know that the best chance is to find 1 student, because we have a 50% chance of finding 1 student, 25% of chance of finding 2 students, and 25% of chance of finding 0 students in the classroom. So at least we could guess 1 student, and that would be our best chance. Now, if we have a macroscopic number of chairs, for example, if we have 10 to the power of 23 chairs, then it is guaranteed that we're going to find 10 to the power of 23 divided by 2 students. In other words, if we have a macroscopic number of chairs, then it is basically guaranteed that half of the chairs will be occupied by a student. For the same reason that if we toss a macroscopic number of coins, it is guaranteed that we're going to find half of the coins with tails up. Now, let's think of another way to interpret this result. We find that half of the chairs will be occupied because the number of students is actually the sum of the probabilities of each chair to be occupied. In this case, the probability is 0.5. So if we get 0.5 times 10 to the 23, we get 10 to the power of 23 divided by 2. In other words, we can find the number of students by adding the probability of occupation of each chair as long as the number of chairs is macroscopic. So we can generalize this result even for a classroom where the probability of occupation of each chair is different. So let's suppose that we label the chairs with the number n. And P of n here is the probability of occupation of the chair n. If we have m chairs and if m is a macroscopic number, then we can say that the number of students will be given by the sum of the probabilities of occupation of each chair, as long as the number of chairs is macroscopic. Now, We can apply the same idea to our problem. In lecture 12, we learned that the probability of occupation of an orbital is given by the Fermi-Dirac distribution. And the most common form of the Fermi-Dirac distribution is this form, and this form is the one we're going to use. But you cannot forget that this is the probability that an orbital, a specific orbital with energy epsilon, will be occupied. Now, since the semiconductor that we are interested is a macroscopic object, we're going to have a macroscopic number of orbitals in the conduction band. So to find the number of electrons in the conduction band, we can sum the probability of occupation of each orbital, and since this number of orbitals is macroscopic, we're going to find that the result is virtually exact. So we're applying the same logic that we applied for the number of students in the chairs now to the orbitals in the conduction band. But instead of the number of students, we are going to calculate the number of electrons in the conduction band. So we're going to sum the probability of occupation of each orbital. So CB here stands for conduction band. So this sum must be performed over the orbitals of the conduction band. And F of the energy here is the Fermi-Dirac distribution. In other words, it is the probability of occupation of each orbital. But before we embark on the calculations, we need to adapt the notation a little bit. Now recall from lecture 12 that we were using this symbol for the Fermi level. But in the literature on semiconductors, this symbol is usually used for the mobility. So we're going to replace it with this symbol. So this symbol now is the symbol for the Fermi level. And the number of electrons in the conduction band we're going to represent with this symbol, N of E. So N of E is the number of electrons in the conduction band. So it is the number of free electrons. So using the new notation, the Fermi-Dirac distribution will read like that, where this term is the energy of an orbital in the conduction band. Now, to evaluate the sum, we need to find the orbitals of the conduction band. So recall that I mentioned in the previous lecture that free electrons, in other words, electrons in the conduction band, they interact very weakly with the underlying atomic structure. So that means that the electrons in the conduction band, they behave essentially as an ideal gas. And in lecture 7, we found that the orbitals of an ideal gas, they are labeled by three natural numbers, and their energies are given by this expression. And this is a kinetic energy. It comes from the classical expression for the kinetic energy. So we already know what are the orbitals in the conduction band. They are labeled by three natural numbers, and they represent the kinetic energy of a gas of electrons. But we need to do two modifications in this expression. So the first modification has to do with the effective mass. So recall that I mentioned that the interaction of the electrons with the underlying atomic structure is weak. But that's not to say that it does not exist. There is an interaction, but we can capture the effect of the interaction replacing the mass of the electron with its effective mass. So the concept of effective mass is quite profound, is quite important in semiconductors, but we don't need to go deep into it. All we need to know is that it captures the effect of the interaction with the underlying atomic structure. And this is a bit like, let's say we want to do physics in a swimming pool. We want to study the dynamics of objects in a swimming pool. We could take into account the interaction of the object with the water, replacing the mass of the objects with an effective mass. So it's more or less the same concept here, but because electrons are waves, the concept of effective masses is quite rich. It can describe quite rich physics in general. But for us, it's going to be a parameter, something given. We're going to look up a table to find the effective mass. The second modification we need to do is related to the fact that this expression is actually a kinetic energy. But here we also have a potential energy, which is the energy on the bottom of the conduction band, which we are calling epsilon c. So our reference energy can no longer be zero because the minimal energy of the electrons here will be epsilon c, it will be the energy on the bottom of the conduction band. So you can understand this energy as being the energy that is trapping the electron in the semiconductors, the potential energy that's preventing the electrons from flying away from the semiconductor. Or you can just interpret this as being a new reference energy. So it can no longer be zero, it has to be epsilon c now because that's the minimal energy we have in the conduction band. And since we are already giving names to reference energies, we're going to use this symbol for the highest energy in the valence band. And recall that this distance here gives the band gap. So we're going to represent the band gap with this symbol. And of course, the band gap is given by this energy minus this energy. Okay, so using these two modifications, we replace the mass with the effective mass. And we take into account that our new reference energy is no longer zero, but epsilon c. So this gives the low energy reference of the system. So with these two modifications in this expression, we have an expression for the energy of each orbital. So we know that the orbitals will be labeled by Cx, Cy, and Cz, and each orbital, in other words, each specification of these three natural numbers would have this energy. So taking this into consideration, then this sum is reduced to a triple sum of covering all possible combinations of natural numbers, in other words, all orbitals, and this term here is this term. So it's given by this expression. So this is the energy of a given orbital specified by a given combination of natural numbers. Now, you may have noticed that we have a number 2 here. So this number 2 is due to the spin. Remember that in reality, each natural number specifies two orbitals, one with spin up and another with spin down. So now we need to take into account this effect. But it's very easy to take it into account. We just multiply everything by 2 because each combination here is specifying two orbitals. Now we can simplify the sum using the so-called Boltzmann approximation. So typically in semiconductors, this term here is much larger than 1. And in the textbook, there's an example for silicon. So if you consider that this number is much larger than 1, we can just ignore the 1 here and simplify this term like this. So this is the simplified version of the Fermi-Dirac distribution. So if we replace this term with this term and send the exponential to the numerator, we obtain this term. So this is the sum that we need to evaluate. So we can begin by replacing the energy with the expression we derived explicitly. So I'm doing this in this passage. So in this passage, I'm replacing this term with this. Now next, we can consider that these two terms here are only numbers, they are constants. So they do not depend on Cx, Cy, and Cz. So we can take them out of the sum. So the sum now is reduced to this simplified term. And to evaluate this sum, we actually can convert it into an integral. And to do that, recall that Cx, Cy, and Cz, they are natural numbers. So the step in the summation is 1. When we go from Cz equal 1 to Cz equal 2, we have a step of 1 unit. Cz equal 2 to Cz equal 3, we have a step of 1 unit. So we can represent these steps explicitly as variations on the variables Cx, Cy, and Cz, recalling that each one of these steps is a unit. So we are just multiplying everything by 1 times 1 times 1. And it's typically the case that this function varies very slowly with respect to a unit step. If this function varies very slowly with respect to these steps, that means that these steps can be treated as if they were infinitesimal steps, because essentially an infinitesimal step of a function is a step where the function does not change too much. And that's the case for this function. When you change the numbers from 1 to 2, for example, or for n to n plus 1, then the function does not change significantly. But if we can treat these terms as infinitesimal steps, this is essentially a Riemann sum. So we can readily turn it into an integral. So we can replace the Riemann sum with its integral version, and then all we need to do is to look up at the table to solve the integral. So I'm just going to quote the result here. You can check this for yourself looking at an integral table. Right, so now that we solved the sum, we have a result for the number of electrons in the conduction band. In other words, the number of free electrons. Now we can just rearrange things a little bit. So from here to here, I just move this part over here to reorganize the expression. And recall that what we want is the concentration of free electrons. So this term is the number of free electrons. The concentration is the number of free electrons divided by the volume. But this term here is the volume. Remember, we are considering a cube. So the concentration of free electrons, which we represent with the letter n, now reduced to this expression, which does not depend on the geometry of the semiconductor anymore. Now we usually define a symbol like NC to represent this term. So using this definition for NC, the concentration is expressed like this. So this is a major result in the physics of semiconductor devices. We're going to use it a lot in this course. And I want you to notice the connection between the concentration and the Fermi level. Recall in the lecture about chemical potential that we mentioned that the higher the chemical potential is, the higher the concentration is. But we did not have, at that time, an explicit expression connecting the chemical potential and the concentration. But now we have. The chemical potential here is appearing in the guise of the Fermi level. Remember that the Fermi level is the electrochemical potential. Since there are no electric fields up to this moment, you can interpret the Fermi level here as being only the chemical potential. And notice that we have a negative sign here and a negative sign here, which means that the concentration increases exponentially with the chemical potential, with the Fermi level, like we expected. So as I mentioned, this is a very important result, and it is so important that we're going to derive it again next time but now using the very important concept of density of states. So I see you next time.